And it's my great pleasure to present Professor Grigory Chechkin from Moscow State University. And the title is here on the screen. So we really appreciate Professor Chechkin that you agreed to deliver a talk at our seminar. Thank you very much, and please go ahead.
Okay, hello to everybody. And first of all, I want to thank the organizers of the seminar or leaders of this session for the invitation to give a talk. It's a pleasure for me. And today I'm going to tell you about some results, which are joint results with Yuri Alkhutov, Vladimir Mazia, Tatiana Chechkina, and Mushfik Aliyev. I'm going to tell you about higher integrability of the gradient of solutions of some elliptic problems. So it should be noted that Boyarsky-Meyers estimates or higher integrability means the following. So if we have, for instance, the second order linear elliptic equation with the right-hand side f, roughly speaking, divergence of f, then everybody knows that we can have the estimate of the gradient of the solution to the power 2. But it is possible to prove that this power can be increased to 2 plus some small positive delta. If we consider P-Laplacian, it means that this inequality must be modified, and you can see it below. So this is, roughly speaking, the main topic of the lecture. And historically, I must say that usually in Western mathematical schools, these kind of estimates are called the Meyers estimates, higher integrability or Meyers estimates. But I must say that the first paper devoted to this topic was published in Mathematical Zbornik by Bogdan Boyarsky. So it's a well-known person, Polish mathematician, and he showed that if we consider the Dirichlet problem, so the Dirichlet condition on the outer boundary, okay, then we can increase the power of the integrability. So he proved that this gradient of a solution is integrable in the power greater than 2. Then later, 6 years later, so it was in 1963, in multidimensional case for the equation of the same type, this higher integrability was proved also for Dirichlet problem, was proved by Meyers. So I think that this kind of estimates one can call Boyarsky-Meyers estimates. Then after that, for the Neumann problem also, some specialists obtained results which are quite similar. And after that, at the end of the 20th century, it was Vasily Zhikov who considered P-Laplacian with variable exponent P of x, which satisfy some special logarithmic condition. And I'll tell you later about this logarithmic condition. One can find these results concerning the higher integrability in these two papers. So after that, of course, you can find a lot of other papers, but it was in some sense first papers. So it was 1997. I must say that Zhikov found this kind of problems in hydrodynamics for non-Newtonian fluids and the problem of thermistor problems. Then Acerbi and Minjone, Diening and Schwarzacher considered the system of elliptic equations with variable summability exponent, and also they proved same results for Dirichlet problem. Quite recently, Anna Balji with her co-authors consider more general situation with functions of the Mackenhaupt class, and also obtained similar results for the Dirichlet problems. But I must say that it's quite interesting to consider not Dirichlet or Neumann problems. It's quite interesting, and I'll tell you later why, mixed Zaremba problem. So it means that we have one part of the boundary with Dirichlet condition and another part with Neumann or Robin condition. So Zaremba considered at the beginning of 20th century, 1910, this situation, and you can see the publication of Zaremba. And using the potential theory, he showed that there exists a unique solution of such problem for the Laplace equation, and I must say that he has quite special assumptions on the Neumann part of the boundary. Okay. Then Fichera, at the mid of 20th century, proved that at the junction, at the neighborhood of the junction point of Dirichlet and Neumann data, the solution lose the smoothness. So, and the problem then a lot of mathematicians then consider this situation, and especially I must say about the Mazia works in this direction about the smoothness losing of the solutions. Okay, so the problem, which is quite interesting, and they are quite interesting for me, because I'm a specialist in homogenization theory. So I need some results concerning this higher integrability, and I'll show you how to apply our results to the homogenization theory also. So about this boundary homogenization of Zaremba problems, I can mention the following paper. So it was Alain Damlamian and Lita Tsen in 1987. Then it was my paper in 1988, and Miguel Lobo and Maria Eugenia Perez. It was also in 1988. So it was just first papers concerning this boundary homogenization of Zaremba problems with a rapidly oscillating type of boundary conditions. Concerning the Boyarsky-Meyers inequalities, I can say that we, together with Yuri Alkhutov, started to study this kind of problems and investigating this higher integrability. In 2021, so you can see just first two publications in this area. So we consider the domain with the Lipschitz boundary, and I must say that sorry, if we consider a general domain with the Lipschitz boundary, we cannot apply directly the LP theory. So just to increase this power of integrability. So we consider a general domain with a strong Lipschitz boundary and with quite complicated structure of boundary parts where we have Dirichlet and Neumann boundary conditions. And we prove this higher integrability for the linear elliptic equation of the second order. Then it was a joint paper with Yuri Alkhutov and Vladimir Mazia in the Archive of Rational Mechanics and Analysis concerning the same topic, including some special two-dimensional example of the structure, boundary structure. Then we considered the P Laplacian with the Yuri Alkhutov with the variable exponent P of x. And I'll tell you also a couple of words about this P Laplacian. So first part of my lecture is connected with the linear equation. So we consider linear elliptic operator of the second order. So we have a domain in Rn with a strongly Lipschitz boundary. And our matrix A of x is symmetric and satisfying this elliptic bounds 2. Okay, then we assume that our boundary is divided into two parts. So first of all, we fix a closed part F, where we will have the Dirichlet data, and the rest G is a complement of F on the boundary. So G is open. And we consider the following Zaremba problem. So we have L of U equals to L. L here is a linear functional on the Sobolev space. And then on F, on the boundary, we have the Dirichlet homogeneous condition. And on G, we have homogeneous Neumann condition. Then we define the following Sobolev space. So we have W1, 2 of D and F, which means that we have functions from W1, 2 of D with zero trace on F. Okay. Then, using the representation of functionals, we can define our solution. It's a weak solution. So define our solution by the integral identity 4. So we consider the function u from W1, 2 of D and F, which satisfies this identity for any phi test function phi from the same space. And the components of the vector function f belongs to L2. Here f appears from the representation of our functional L. Okay, so roughly speaking, if we have the Dirichlet problem, not the Zaremba problem, then instead of this functional, we can write just the divergence of f. But in the case of the Zaremba problem, it's not so easy because of course we have some special influence on the boundary conditions. So just we use this functional L and the representation of this functional by means of this vector function f. Okay. As I told you, we studied the question of higher integrability of the gradient, and crucial role here, the structure of f plays this crucial role. So to just accurately define the structure, we need to have the notion of capacity. So if we have a compact set K in Rn, we define the capacity by means of the formula 5. So it's quite well-known situation. If Q is equal to 2, it's just harmonic capacity. But we assume that Q is greater than 1 or less than n, and it can be any of these numbers. Okay, so we have this capacity of compact set. Then, to have some special conditions for our set capital F, we use the following. So we have a ball, and we denote it by B sub r and x0. It means that this is a ball of the radius r centered in the x0, and we consider Q. So for our capacity equals to 2n over n plus 2 if n is greater than 2. And in the plane case, so if n equals to 2, we have Q equals to 3 over 2. And we assume that we have the following condition fulfilled. So this capacity of the intersection of F and the ball BR x0 for an arbitrary point x0 from F must be greater than or equal to a constant C0 times R to the power n minus Q. Okay, so this condition is quite difficult to verify, of course. So we can consider stronger condition 7, which means that this intersection of F and the ball, we have the condition not on the capacity of this intersection, but on the n-1 dimensional measure. And it must be greater than or equal to also the constant C0 times R to the power n-1. I must say that this condition 7 is in some sense universal. So in any situations for linear equations, for P-Laplacian, for some equations with shift, so for any different situations, this condition is good. So if it is fulfilled, we'll have our Boyarsky-Meyers estimates. And the condition 6 is much more delicate. And I must say that for any situations, we have different conditions for the capacity. So here, for the two-dimensional linear elliptic equation, we have the condition 6 in the following form, as I told you. Okay. Then, both the condition 7, which is stronger, and 6 just lead to the satisfaction of the Friedrichs inequality. So we have this integral of v squared less than k times the integral of the gradient of v squared. Then immediately just applying the Lax-Milgram lemma or Lax-Milgram theorem, we can obtain the unique solvability of our problem. Okay, so the result is the following. If our vector function f belongs to L2 plus delta 0, so each component, of course, where delta 0 is some positive constant, then there exists two constants, so delta, which is less than delta 0, and c, which depends only on this delta 0, the dimension, our constant C0 from the condition on capacities, and also the constant R0 and this is a constant from our condition on balls. Okay, so just the balls must be of radius r, which is less than this constant. Okay, such that we have the estimate. So the integral of the gradient of u to the power 2 plus delta is less than the integral of modulus of f to the power 2 plus delta. Okay, so that this is for linear equation of the divergent form. Now, linear elliptic operator with drift or shift. We have the following. So we consider the operator 9. So we have this divergence of A times the gradient of u and plus B times the gradient of u. So we have these additional terms, and we need some additional conditions for this constant B, because B is a vector function. And of course, the first term is elliptic, so also we have the symmetric matrix with this condition 10. And for B, we have the following assumptions. So if we have the plane case, so it means that n is equal to 2, then our components B1 and B2 belongs to LP, and P must be greater than 2. But if n is greater than 2, so we have a special case, okay, 3 and more, then of course it's quite easy to show same for P greater than n. But we proved also for the critical Sobolev constant P equals to n. And we consider this situation just now. Okay, so just P is greater than or equal to n. Okay. Then we consider similar Zaremba problem. So we have also closed part of the domain, which we denote by F, and the complement G. We consider also our operator, which we defined just now, in the domain D. U is equal to 0 on F, and the Neumann condition, homogeneous Neumann condition on G. In the same way, we define our Sobolev spaces. So it's a Sobolev space with functions which is equals, which trace equals to 0 on F. And also we have the integral identity. So we consider weak solutions. So it's a function from this Sobolev space, which satisfies the integral identity. And F also is just the vector function from with components in L2, which appears from the representation of our functional L. Now we have the following assumptions on this capacity. So also we have our ball B Rx0, where x0 is an arbitrary point from F, and R is less than or equal to R0. So we have the following inequalities. If n is greater than 2, we have this capacity, the capacity of the intersection of F with any balls with an arbitrary point x0 greater than or equal to the constant times r to the power n minus q, where q is 2n over n plus 2. And if n is equal to 2, then we have the same inequality where q1 is equal to p over p minus 1. Okay, so this conditions 14. Same situation, so we need to have our Friedrichs inequality, and then it is possible to prove the theorem of existence and uniqueness of solutions. And the theorem just have completely the same form. So if f is a function from L2 plus delta 0, then there exist two constants, delta, which is less than delta 0, and c, such that we have the inequality 15. Okay. Now, how to apply this Boyarsky-Meyers estimates for some problem with a rapidly changing type of boundary conditions. So we consider also the Zaremba problem, and we have this bounded domain with Lipschitz boundary, and on the boundary we have the parts, small parts, f sub j. The length of these parts equals to epsilon, and if epsilon goes to 0, then the number of these parts just growing. So it means that the number is not fixed. We have growing number of these parts, and it means that now to define the our set F, we have the following notation. So just we denote by m sub epsilon the number of these parts fj, and f is the union of fj for j from 1 to this m sub epsilon. So m sub epsilon is a number which is growing to infinity as epsilon tends to 0. And we consider in the domain D the following problem. So we consider the Poisson equation. On F, we have the Dirichlet, the homogeneous Dirichlet condition, and on J, instead of Neumann, just I prefer here to have the Robin condition, because I want to consider the situation when the limit problem as epsilon goes to 0 just keeps only the Robin condition. Okay, so just this Dirichlet condition will disappear when we pass to the limit. So finally, we have this given problem 16 and the limit problem or homogenized problem 17. And it's quite easy to show that we have the convergence of the solution U to the solution U sub 0. But the problem and the main question is to estimate the rate of convergence. Usually for some applications, we need this rate of convergence, not just the fact that we have this convergence. So how to do it? The first step is the following. So it's quite easy to show that our family of solutions U is bounded in the Sobolev space. It's just using the integral identity. It's quite easy to do, and using the some integral estimates. Then, if it is uniformly bounded, we have, of course, a weak limit. We denote it by U sub 0, and then it is possible to show that U sub 0 is the weak solution of our problem 17. Okay, so this is the first step, and just in some sense, I omit the details of this step. Then, to estimate the difference between these functions, U and U sub 0, we use the following approach. So we have the cutoff function psi of s, which is equal to 0 as s less than or equal to 1, and 1 if s is greater than or equal to 1 plus some small sigma. Then we consider the polar coordinate system around each part fj. So we have this polar radius r sub k, so it means that it's part fk, okay? We have this radius, and we just substitute instead of s, this logarithm of epsilon over logarithm of rk in the modulus of this ratio. And this is a function psi sub epsilon k. Then we consider the product of these functions, and we denote it by psi sub epsilon. So this function is equal to 0 in some small neighborhood of each part f sub k. Okay, now considering an arbitrary function phi from the Sobolev space W12 of D, so just which has no zero trace, okay? Then we multiply it by psi sub epsilon, and we obtain the function which we denote by phi sub epsilon, which belongs to the space W12 of D and F, so having the zero trace on our set F, okay? Then we just subtract one integral identity from another, substituting in the limit integral identity the function phi, and in the original the integral identity the function phi sub epsilon, so this product of phi and psi sub epsilon. And after some simple transformations, we have the following estimate. So we have the norm in the Sobolev space W12 of D of the difference U and U sub 0, which is less than or equal to a constant, just independent of epsilon, of course, times the sum of two integrals. So first integral is f times the gradient of phi times the difference between psi sub epsilon minus 1, and the second one, gradient of u times the gradient of psi sub epsilon. It's quite easy to estimate the first integral, because it's quite natural to have this just the area of our semicircles around the parts fk, where psi sub epsilon is not equal to 1, okay? And so you see it's just some constant k times the square root of the number of these parts, and times the square, I mean the area of our semicircles. So epsilon to the power. So this is a power estimate in some sense. Okay. Now we need to estimate the second term. So gradient of u times the gradient of psi sub epsilon. So first we we shall estimate this integral just without Boyarsky-Meyers estimate. So we have this standard Cauchy-Schwarz inequality, and the second integral, so integral of the gradient of psi sub epsilon squared, it's quite easy to calculate just directly because we know the structure of our cutoff function. So it would be the following. So we have some constant k1, then we have the square root of our numbers of parts, then the logarithm of epsilon, modulus of logarithm of epsilon, and this integral, which can be calculated directly. So it's d logarithms of r over the logarithms of r to the power 4. And just calculating, we obtain the following estimate. So we have this some constant, then square root of the number of parts, and the logarithms of epsilon to the power minus 1/2. So it means that to obtain some reasonable estimate, we need to have logarithmic number of parts. And you can see it. So it's a logarithm of epsilon to the power 1 minus theta, where theta is positive and less than 1. Okay, so logarithmic number. Now, using the Boyarsky-Meyers estimate, we can do the following. So we use here the Hölder inequality, where P1 is greater than 2, because we have this higher integrability for our gradient of the solution, and P2 which is less than 2. Now we can do just the same procedure, just calculating directly. Finally, we have some constant K2, then the number of our parts to the power 1 over P2, then epsilon to the power, and logarithms of epsilon to the power. So it means that if we want to have a logarithmic rate of convergence, we can consider the number of our parts, which is power. So it's epsilon to the power. Or if we have, if we want to have some epsilon to the power rate of convergence, then we can take the number of parts just logarithmic, or just both. We can have both, and rate of convergence and the number of parts just epsilon to the power times logarithms of epsilon, also in some power. So, so we have, you see, using the Boyarsky-Meyers estimate, we have much more perfect rate of convergence and number of these parts. Okay, now the next step is connected with the P of X Laplacian. So we have the variable exponent P, and it's our joint paper with Uriel Hutov. Also, it's a paper of 2023. So let us consider P of X Laplacian, and to define it, we say the following. So first of all, P of X is a function which is greater than alpha, which is a constant greater than 1, and less than or equal to beta, also a constant. Then we need to define some functional spaces to say something about the solutions. So we consider the space which we denote by W. It's a function V from the Sobolev space 1 alpha of D, such that the gradient of V to the power P is a function from L1 of D. And we use the following Sobolev-Orlich norm. So the first term is classical L alpha norm of V. And also we have Luxembourg norm of gradient of V, which is defined in the following way. So we have the infimum for t greater than 0, the positive t, of the integral of the modulus of g over t to the power p of x, ex, and it must be less than or equal to 1. Okay, so this is a Luxembourg norm. So finally we have the Sobolev-Orlich norm, and using this norm, we obtain the reflexive Banach space. So W just becomes to be this reflexive Banach space. And we denote it by W1 P of X of D. And in the same way as we did before, we consider the functions from this space with 0 trace on F. And at the same time, we can define the following functional space, H1 D of X of D, which is the closure of the set of smooth functions, just using the same norm as we defined, so Sobolev-Orlich norm. And I must say that in this situation, the spaces H1 P and W1 P are different. So, and it was Vasily Zhikov who found this now quite well-known logarithmic condition under which we have the same spaces. So under this condition, the space H1 is identical to the space W1. So this is a logarithmic condition of Zhikov. P of x minus P of y must be less than constant over the logarithm of modulus of the difference between x and y for any x and y quite close to each other from D. Okay, so now we consider the following Zaremba problem. So we have this P of x Laplacian in D, also homogeneous Dirichlet condition of F, and the homogeneous Neumann condition on G, where F also is closed. So we can define both W solutions and H solutions. And as I told you, they are different. So W solution means the following. So we have the function from this space, which satisfy as the integral identity for any phi from L P prime, where P prime is a P over P minus 1 for any test function phi. And this, in the same way, we can define H solutions. So, first of all, we assume the following inequality to hold true. So V in L alpha is less than a constant times gradient of V in the space L alpha. So it's some kind of Friedrichs inequality, which implies immediately this inequality for V in L alpha and gradient of V in LP. So in this with this Luxembourg norm. And finally, we can introduce the new norm 28. Okay, so just because of this inequality, we can introduce a new norm, just gradient of V in this Luxembourg norm. Okay, for both solutions, of course. Now the condition for the capacity is the following. So we have also the capacity of this intersection, which must be greater than or equal to constant times r to the power n minus q0, where q0 is alpha prime plus 1 over 2 and alpha prime is minimum of alpha and n over n minus 1. Or, as I told you, the condition 30. The condition 30 is our previous condition 7. So just I told you that this condition is quite universal. And the theorem is the following. So if we have modulus f to the power p prime, which belongs to L1 plus delta 0, with some positive delta 0, then there exists a constant delta which is less than delta 0 and c, such that we have the following inequality. So the integral of the gradient of u to the power p of x times 1 plus delta is less than or equal to a constant times the integral of modulus of f to the power p prime times 1 plus delta and plus 1. And I must say that this constant c depends only on p, delta 0, c0, and the L1 norm of our function f to the power p prime. And if alpha is greater than or equal to n plus something, some positive nu, then this theorem also can be just proved for f without any additional assumptions on the capacity. So for any f, even if we have only 1 point. Okay, now the final part of my talk. So I have, as I understand, 4 minutes. So I want to tell you about one interesting example. So we consider the three-dimensional case. We have a box, and on the upper part, we have this quite complicated structure of our set F. So we consider the decreasing sequence of positive numbers such that 2L sub j plus 1 is less than Lj. Then we have this first segment delta 1 on the axis x1, sorry. And then we denote by E sub 1 the union of two closed delta 2 and delta 3 of the length L2 containing both ends of delta 1. So we have just two subsegments on our delta 1. And we denote E capital E1, E1 times E1. Okay, so just as a square. Then we repeat this procedure for this segment delta 2 and segment delta 3. So just now the role of L2, this L3 plays the role of L2 in the second step. And also we have this capital E2 squares. And we obtain, as a result, we obtain two-dimensional counter set F, which is the intersection of all these E sub j. In three-dimensional case, Q must be 6 over 5. So the condition of this capacity, positive capacity 31, can be reformulated in our Lj. So we have this inequality 32. Then just choosing small a to the power minus g plus 1 as Lj, and a is from the segment from the interval 2 and 4 to the power of 5 over 9. Then, of course, we have the sequence which satisfies this inequality. 2Lj plus 1 is less than Lj. And reformulating, we obtain the inequality which is just below on the page. So, first of all, it's quite easy to show that the two-dimensional measure of f equals to 0. I think that everybody knows about this one-dimensional counter set, but for two-dimensional it's just the same. Because it's quite easy to see that in each G step we have this 4 to the power J closed squares of this with sides of the length, and it's quite easy to just calculate the area of these squares. And it is possible to show that this 6 over 5 capacity of the intersection is greater than C0 times R to the power 9 over 5, where B is our ball, which we defined before. And here R0 is 1 over A, C0 also could be calculated, and hence we have this higher integrability. So the Boyarsky-Meyers estimate is valid in this case. So you can see, so the capacity is positive and satisfies this inequality 33, and the measure is 0. That's quite interesting. Of course, it is possible to consider other fractal some sets just to satisfy this condition on capacities with, of course, 0 measure. But it's just we did not calculate something for more complicated fractals. Okay, thank you very much for the attention, and it's just my last slide, final slide.
Well, thank you very much, Professor Chechkin, for a very nice presentation. It was really nice to see applications of variable analysis, because we have so many papers on playground calculus, on variable analysis, but a few papers just deal with real applications, So it was great to hear from you such nice pictures and applications and cases. Well, we have time for questions, if any. Meanwhile, people thinking, maybe I have a very short question. I didn't get one issue. Maybe I did focus myself. You have this variable P. You consider it to be bounded on domain, or you can take also unbounded cases?
No, the domain must be bounded.
No, not domain. I mean the exponent
P is just a function which satisfy
the exponent, the exponent P of X.
P of X, and it's a function which must be greater than alpha and less than beta. It's just bounded,
I see.
Bounded function, yeah.
Okay, I see. Okay. And in most cases, I also did some research on variable analysis, and in all cases, I assume these logarithmic conditions, because if you don't assume this condition, you lose so many properties. And you say that you're able to do something even without this condition, right?
Yeah, exactly. You are right, and this is quite interesting situation. It's a Lavrentiev phenomenon when we have different spaces H and W. Yes. And it is impossible to prove this Boyarsky-Meyers estimates. So I need this logarithmic condition. I need.
So basically, you are inside of variable Lebesgue spaces.
Yeah.
Have you any thoughts about kind of variable Morris spaces, which is natural extension?
Yes, of course. We thought about this Morris spaces, and as I told you, this Mackenhaupt classes. Also, it was Anna Baljic who considered. So we have a lot of different directions to generalize these results, and especially for Morris case.
Okay, perfect. Thank you. Well, maybe some more questions. Vladislav.
Not a question, just a comment. Thank you very much. It was really very interesting.
Thank you.
Revealing. Thank you.
I must say that it's quite interesting to apply same technique for the parabolic problems, because also it's quite interesting because of some applications. And now we're working on this parabolic situation.
Okay. Well, maybe some more questions. Presentation was very clear. Thank you.
And I sent to Tatiana Mikhailovna, so you have this presentation.
Yes, we have this, and also we upload a video later, so people can check again, once again. Okay, well, if no more questions, I actually cannot see hands, but maybe some people have questions, but I'm not seeing some hands. But well, as I said, it was our great pleasure to have such a nice presentation. Let us thank speaker for very nice talk.
Thank you.
And still we have one more seminar this year on December 26th. Thanks to everyone who came to our seminar today. Thank to the speaker again, and see you in 2 weeks. Thank you.
Thank you for listening.